Cool. One of the things about this particular chapter is that it's going to be rolled in very nicely with what we do in the next chapter. Bottom line is, if you don't understand what's going on in chapter 17, you're going to be in deep trouble for when we get to chapter 18. Because all we're going to do is take this concept and build right on top of it. Okay. So bottom line is, let's take a step back and make sure we understand some of the basics of acid-base chemistry, because if we don't know that, we're going to be in trouble. All right. So few important things. When we say an acid and a base, it's very important that we understand what the heck we're meaning. Okay. So an acid is a proton donor. And yes, I'm calling this hydrogen ion right here a proton. All right, and let's just take a step back and think of why that might be. Hydrogen, the smallest element that exists. If I got a neutral hydrogen atom in my hand, it has one proton and one electron. If this hydrogen then is going to have a positive charge, is it going to gain an electron or lose an electron? Let's use the chat right now. Are we gaining or losing electrons to form a positively charged ion? What we got? Cool. So it's sort of a tricky one, but remember that electrons are negatively charged, right? So if my ion is positive, then I got to be taking away that negatively charged electron, right? So I have this atom in my hand. It's neutral. It's got one proton, one electron. I take that electron away. The only thing I'm left with is a proton, right? So that's why we call the hydrogen ion a proton, because that's all there is there. The electron's been lost. So that's what an acid does. Okay, they are proton donors. So let's think of an example, a classic example of an acid that you'll use tons of time in your chemistry career is hydrochloric acid. And what does the acid do? It donates that proton. And honestly, I think donor is a little bit kind of a word, because it's not like a gentle, oh, here you go, sir. It's like throwing that proton anywhere it can put it, right? It's trying to get rid of that H. That's what an acid's job is to get rid of that hydrogen. A base is the exact opposite. It's the one doing the accepting of the proton, right? So acid is getting rid of its proton. The base is the one taking it, saying, thank you, I'll take that. Okay, so these simple definitions are very important to have in your mind. They're going to be the starting point for a lot of our conversations on acids and bases. All right. Now, if we have an acid-base equation here, so HCl plus, let's do NH3. What we're going to see is our acid donates its proton to this base. So what's going to happen to my acid? It's going to lose this hydrogen ion. And remember, since that hydrogen it's losing is positively charged, what it's going to leave behind is not just a neutral chlorine atom, but a chloride ion with a negative charge. Okay, and the base is going to be the one picking up that proton, right? So now I'm going to draw my formula for my base, but now notice the difference, right? So let's just play spot the difference here. Here, my base had 3 hydrogens. Over here, now it's picked up that extra one and has 4. But again, it's that positively charged hydrogen ion, so it also gains a positive charge. All right, we have special names for these guys on the other side of our chemical equation here. The acid is going to become the conjugate base. And the base is going to become the conjugate acid. Okay, so given an acid and a base, the first thing you need to be able to do is figure out the products of this reaction, right? If I'm giving you these reactants and I'm saying, what are the products? That's going to be the starting point for a lot of what we do, right? So just being able to say, here's an acid, here's a base, what are the products? That's like an important first skill that we need, or we're in big trouble moving forward. And let's just kind of make a little note here about how exactly I got my conjugate base. Right? Starting with acids, starting with my acid, I remove a hydrogen. And then what happened to the charge? I decrease charge by 1, right? I'm subtracting 1 from the net charge to get my conjugate base. And then if I'm doing my conjugate acid, I'm going to do the exact opposite. I'm going to start with my base, but I'm going to add a hydrogen, and I'm going to increase the charge. Add 1 to the charge. Okay, so being able to predict the products of an acid-base reaction is like step 1, or we're in big trouble. All right, so let's just make sure we got that skill down. I'm going to give you another acid and base combination, and you're going to tell me what exactly the conjugate acid and conjugate base are. All right, so let's use, we're going to make it a little bit trickier. This is going to be playing the role of our acid. And then we have one of the most commonly used bases in the lab over here, the hydroxide ion, no doubt one that you'll be using this semester, is our base. So take a minute and give me what the conjugate acid and conjugate base are for this reaction. All right, so for my acid, right, to get my conjugate base, whoops, that's not what I meant to do. I'm going to start with my acid, which is that HSO4 with the -1 charge. I'm going to take away a hydrogen. So now I just have SO4. And I got to decrease that charge by 1. Since I started out with this negative, since I started out with this -1 charge, now my net charge will be -2. All right, so this is my conjugate base. To get my conjugate acid, I'm going to do the exact opposite. I'm going to take my OH and I'm going to add a hydrogen. This gives us water. And I'm going to increase the charge by 1. So it goes from so it goes from -1 to 0. When it's 0, we don't bother writing the charge. All right, so this is now my conjugate acid. All right, so again, just kind of trying to review some basics here. The next thing that we need to know is the difference between strong versus weak acids and bases. Okay, being able to spot these are going to be important. The difference between the two, if you're just going to kind of like explain to someone what the difference between a strong acid and a weak acid is, strong acids will fully dissociate. And what I mean by dissociate is break apart, right? If I take, for example, HCl, put it into water, 100% of those HCl molecules are going to successfully donate that proton right? So this reaction goes 100% to completion. Weak acids, on the other hand, do not fully dissociate. So if we take, for example, a weak acid, I don't know, like we'll do something like this. Okay, and how do I know this is a weak acid? We'll go over that in just a second, but you're just going to trust me that this is a weak acid. Yeah. And we put this into water. The whole point being is that this is now a dynamic equilibrium. This reaction does not go 100% to completion. There's a good bit of this back reaction or this reverse reaction that's happening as well. Let me just make some room. Sorry. All right, too big. My products, I can still predict. Right? So actually, everybody take a minute. If this is my acid and this is my base, predict the products of this acid-base reaction. The acid is going to lose a proton. And this is kind of always a little bit tricky. It's always going to be the hydrogen that's at the very front of the formula or the very back of the formula. So for in this case, it's going to specifically be this hydrogen, not these ones in the middle here. We write the formula for acids in such a way that the H that's being donated is always at the very front or the very back, right? And always by itself. So my conjugate base would be when I'm going to have to write it down here, would be when I subtract a hydrogen and decrease the charge by 1. And my conjugate acid would be when I add a hydrogen and increase the charge by 1. All right, so conjugate base, conjugate acid. All right, and again, the whole shtick about a weak acid is that this is a dynamic equilibrium. These reactions are happening back and forth, meaning you're not going to get full, complete dissociation. There's always going to be some of this left behind, some of that whole acid molecule. All right. Same concept goes for bases. Bases, strong bases will fully dissociate, whereas weak bases, you have this dynamic equilibrium that you have to worry about. In terms of acids, strong acids. The bottom line is how we spot a strong acid is there's this short list that we just got to know. All right. The most common one, again, that you're going to see used a lot is HCl. The other halogens in that column, right? So if we look on the periodic table in that column where chlorine lives, all the other halogens, that's what that column's called, HBr and HI are also strong acids. The other three are HNO3, HClO4, and H2SO4. That is our list of strong acids. All right, some lists, some textbooks differ. They also put this guy on the list as well. Let's just stick to these 6, make our lives a little bit easier. All right. There's some discrepancy in certain textbooks. So we're going to just... Cool. So basically, if you have an acid and it's not on that list, everything else is a weak acid. All right. So we got that short list of 6 strong acids. Anything else that's not on that list, it's going to be a weak acid. All right. So with strong versus weak bases, These are actually a little bit easier to remember. So let's make our cheat sheet list here. Strong base versus a weak base. A strong base is any soluble ionic compound with a hydroxide ion, right? OH minus is hydroxide. So anytime you got a salt with a hydroxide ion, that thing is going to be a strong base. All other bases are considered weak bases. And to be honest, 99% of weak bases, so all else, but they sort of have this very common feature that we're going to see over and over and over again, and that is nitrogen acting as a weak base. Right, so a lot of weak bases have a nitrogen in them. The nitrogen, the lone pair on that nitrogen in particular, is the thing that's stealing that proton from the acid. Cool. All right, so now we're going to dive into sort of the quantification stuff. We did a little bit of this last time working with pH and autoionization. If you look back in your worksheet last time, there was a difference between how we did the pH of strong acids versus the pH of weak acids, right? So in terms of pH calculations, for strong acids, because they fully dissociate, we just say that the concentration of the acid that we start with is going to be equal to the concentration of hydronium ions at equilibrium, right? After you added it to the water. So whatever your starting concentration of acid is, that's the concentration that you plug into the pH formula. Remember, pH is the negative log of that hydronium ion concentration. So if I'm given an initial concentration of acid, and I'm just going to assume that it's the same as the concentration of hydronium ions at equilibrium because it's a strong acid, I just plug that value into my pH formula. Weak acids are much more difficult of a calculation. Those would be the last two calculations we did on that last worksheet. Weak acids, we have to account for the equilibrium, right? Account for that equilibrium using that equilibrium value, the Ka, right? These were much more intense calculations because we had to use those ice tables. Okay, so pH, if I give you pH of a strong acid, best case scenario, turn around, plug that concentration into your negative log formula. If I give you the pH, if I ask for the pH of a weak acid, all of a sudden we got to do a little bit more algebra incorporating the Ka of that because, again, there's this dynamic equilibrium where not all of that acid has dissociated. I can't make this assumption anymore. Cool. So that's what we're going to pick up with today, is now focusing on bases. Okay, so basically exactly what we did last class, but now we're going to be determining the pH and pOH of bases. So first of all, pOH, let's go over a few formulas real quick. The P always means the same thing. It means take the negative log, right? So pOH is now the negative log of, instead of the concentration of hydronium ions, it's the concentration of hydroxide ions. Remember, we had this autoionization relationship. Where if you know the concentration of I should be consistent here. Some textbooks just use H+, which is honestly what I'm used to, but I know y'all's uses the hydronium ion, so I apologize. I'll stick with that. The hydronium ion concentration times the hydroxide concentration is equal to that 10 to the negative 14. right? That is this auto ionization relationship. So if we know one, if we know the hydroxide ion concentration, we can always figure out the hydronium ion concentration. We can actually put this into the world, the magical world of logarithms, as my former math professor said. Logarithms have a very weird algebra behind them, right? Multiplication, if you take it into the world of logarithms, it's actually addition. I'm sure everybody is log experts, but nonetheless, just to review, we can take the log of both sides, and then we get this new relationship where we say the pH plus the POH is just equal to 14. All right, so with that in mind, everybody take a minute and see if you can't answer these few questions for us here. All right, and to kick things off, what we're going to need to do is we're going to need to look at this base right here, sodium hydroxide. I want everybody to use the chat and tell me whether this is a strong base or a weak base. And because it's a strong base, this is kind of like best case scenario. Now I just get to assume that my initial concentration of sodium hydroxide is equal to that hydroxide concentration at equilibrium, right? I don't have to do any extra math with pKa's or pKb's, equilibrium constants. All right, so everybody take a minute, see if you can't give me the pOH of this solution and then the pH of the next solution. Cool. Yeah. So let's see. For one, if you get your answer, let's pop it into the chat here. Cool. All right. So if I can make this assumption, then it's as easy as, well, the pOH is going to be equal to that negative log of 0.235. Punch that into my calculator, and I get 0.62893. Okay, and actually pH is one of these odd unitless quantities. It always bugs me out to see that number just floating by itself, but that's how pH works. And then so finally, and actually this is the answer key is actually not quite right here in the sense that if I'm being good about sig figs, my concentration has 3 sig figs, which means that I need to have 3 decimal places on my POH here. So really it should be 0.630 if I was really being good about sig figs. Okay. Remember, this is because we have this new log operation. The number of sig figs in my concentration is equal to the number of decimal places in my pH and now POH. All right, so now now the next one here, everybody take a minute. Once you think that you have the correct answer, put it in the chat. For number 2, the big difference here is it's asking for the pH. All right, I will also say there's one other tricky little bit here, which is the fact that there's not just one hydroxide ion on that barium hydroxide, but 2, and you have to account for that. So let's see how well we do. Awesome. Okay, so this is asking for the pH, but I have this strong base here, right? So I'm going to have to use this relationship that the pH plus the POH is equal to 14. If I can find my POH, then I can rearrange this equation really easily to solve for the pH, right? So then the first thing I'm going to need is the POH. Again, I have my concentration of my barium hydroxide initially. This is going to be equal to 2 times the, I lied. Rather, the concentration of hydroxide ions is going to be equal to 2 times that barium hydroxide concentration, because each barium hydroxide has 2 hydroxides, right? So I got to account for that mole fraction there, rather mole ratio. So my concentration of OH minus is going to be 2 times the 0.116. All right, so that's what I'm going to plug into my negative log formula. My POH equals the negative log of 2 times 0.116. That gives me a POH of 0.634512. So now I'm going to turn around and just plug that POH into my formula here. So if I take 14 minus that 0.634512, that's how I get my pH of 13.36548. I'm going to make more room for myself here. 36548. All right, and then so y'all said C, that's correct, but what if I did this to the correct number of sig figs? Let's use the chat here. What would my value be at the end of this calculation to the correct number of sig figs? All right, so I'm going to look at how many sig figs there are in my initial measurement, which was 3. That's going to correspond to the number of decimal places in my pH. So I'm going to round to this decimal place here. So 13.365. All right, so the next, and I guess just to take a step back, these first two problems, really the thing to hammer home is this intimate relationship between hydroxide ion concentration and hydronium ion concentration, or pH and pOH. If you know one of those, you can figure out the other one. All right. I think the hardest part for students, or where students get tripped up the most, is just not really thinking about what they're punching into their negative log. You put a concentration in there, but the concentration of what, right? You got to pay attention to what you're punching in there. Is it the concentration of hydronium ions or the concentration of hydroxide ions? All right, so for this next problem here, it's asking for which of the following would form a acidic solution in water. Okay, and it gives this list here. None of them are strong acids, that's for sure. So how are we going to spy which one of these forms an acidic solution in water? Let's go back to what we did at the beginning here. All right, and I'm going to make some room by getting rid of this one. The first thing we covered today were these conjugate acid and base pairs, right? Given an acid and a base, how do I figure out the conjugate acid and the conjugate base? But now let's go into why they're termed that way. Why is there this terminology to begin with? Well, the conjugate acid is called the conjugate acid because now it has an extra proton. So if I were to do the reverse reaction, NH4 plus and Cl minus going to HCl and NH3, it's because in the reverse reaction, now this thing is playing the role of an acid. And the conjugate base is termed the conjugate base because in the reverse reaction, it's playing the role of the base. Okay, so now this is my conjugate acid. And this is my conjugate base. All right, so again, where does that term come from? Conjugate acid, conjugate base. It's because in the reverse direction, that's the role that that molecule would play. All right, so what we need to sort of note here is that there's this inverse relationship between the strength of an acid and its conjugate base. What do I mean by that? Strong acids have very weak conjugate bases. And actually, let me just specify, not just weak, but very, very, very weak. So for example, HCl, the conjugate base, Cl minus, chloride is an absolute trash base. It won't accept a proton if they're giving them away for free. All right. So this would be what we would call a neutral compound, meaning it doesn't have any effect on the pH. But if we have a weak acid, so for example, we'll take our H3COOH. It's got a weak conjugate base. All right, and we'll call it like a stronger weak conjugate base, CH3COO minus. All right, and so what do I mean here? This would still be considered to be a weak base, but would absolutely have an effect on the pH, right? If I took, for example, a salt that contained just this and dissolved it into water, it would actually be playing the role of a weak base. It would it would increase the pH of that solution. Okay. Part of why we have to use that Ka value, part of why we have to use that equilibrium to take into account, right? So again, strong acids, kind of best case scenario, makes our life easier. We don't have to worry about what this thing over here is doing, the conjugate base. But if we start out with a weak acid, all of a sudden that conjugate base is going to be, you know, not neglectable. We can't just neglect its effect. So likewise, we have the same thing. If we have a weak base, like for example, that ammonia, it's going to have a stronger weak conjugate acid. Meaning the conjugate acid can play the role of a weak acid, right? It can, whoa, where did I go? It can actually donate that proton. So let's go back to our problem here and let's see. We can't spy this ammonium ion right here is going to color. What's going on? There we go. Is going to be the one that can actually form an acidic solution in water. This can donate that proton because it is the conjugate acid of a weak base. All right. Let's go to our next one here. So this says that it wants to know the Kb of this cyanide ion. All right, given the Ka of the acid form. All right, so if HCN is my acid, the conjugate base is that what's called a cyanide ion. And how did I get that? Remember before what we did at the very beginning. I took a hydrogen away and I subtracted one from the charge. All right. And there's this relationship between Ka and Kb, right? The Ka of an acid and the Kb of its conjugate base. That goes to our autoionization relationship. Ka times Kb is equal to that Kw, that 10 to the negative 14. All right, so that autoionization relationship, creeping back again. If we know the Ka of a compound, we can always find its Kb and vice versa. All right, and so punching that into my calculator, if I take 10 to the negative 14 divided by that given Ka, I get the Kb, which is equal to this 2.0 times 10 to the 5th. All right, so now for this next one, now we have a weak base. So all of a sudden now we can't just assume the concentration of hydroxide ion is equal to the concentration of our starting base. We got to incorporate the equilibrium constant. So the first step is to get, and this is why we did this at the very beginning, is to get your balanced chemical equation. If we put this base, ammonia, into water, everybody get, and actually we'll do the dynamic equilibrium arrows here. If this is my base and this is my acid, everybody complete this balanced chemical equation. I'm actually going to take this to a different place so I got more room. All right, so how are we going to do these weak base problems? And it's actually the same procedure for the weak acid, but let's just sort of write it out here. First, we need our balanced chemical equation. This is specifically for calculating the pH. All right, so again, what do bases do? Bases accept protons. So my base is going to accept a proton, turn into its conjugate acid, the ammonium ion. And what is our acid going to do? It's going to donate a proton, become its conjugate base. All right, so step one, get that balanced chemical equation. Step two, we need to set up, sorry, our equilibrium expression. Right, so here's our equilibrium constant, Kb. And when we set up our equilibrium expression, what do we remember? What over what? Where did the water come from? That's a great question. Because anytime we have a solution, right, this molarity here, the solvent is water. So anytime we're talking about a solution of acid or base, it's always in the presence of a huge amount of water. And so the base, when it's changing the pH of that solution, it's doing so by reacting with the water molecules in that solution, right? Remember what a solution is. That means that I take some solute, which is either my acid or the base, and I dissolve it into my solvent, which is water, right? So anytime we're talking about a solution of acid or base, there is a crap ton of water molecules floating around. 99% of that solution is water. And it's the reaction of the acid or the base with the water that's changing the pH of the solution. So that's why when we're figuring out pHs, we're always looking at reactions of our acid or base with water. We did the same thing last class when we were talking about acidic solutions. We took our acid, reacted it with water, and calculated the concentration of the hydronium ion at the end. Here we're going to play kind of like the analogous game where we're going to take our base, react it with water, and figure out the concentration of that hydroxide ion. All right, but very good question. So equilibrium, what you're going to remember, the key to life here, products over reactants, right? Products over reactants. That's the one thing you should be chanting to yourself anytime you're building an equilibrium expression. We're going to put our products, the concentration of those products, right? That's what those brackets mean, is concentration. Over our reactants. Right? And this is where we actually exclude the water, kind of for the same reason that I was talking about before, because there's so much water floating around in this solution that the concentration isn't going to change. Meaning if I add a few water molecules or take away a few water molecules, there is just so much water that that's going to have a negligible impact on the actual concentration of the water, right? So the concentration of H2O is going to be constant. So we're not going to include it in our expression. It's not going to change. All right, so step two, we have our equilibrium expression. We have this from the problem, right? That value is given to us. The problem is, what the heck goes here, here, and here, right? And for that is why we use our ICE table. We're going to have to look at the initial concentration of everything in our equilibrium expression. So the concentration of base, concentration of hydroxide, and the concentration of the hydronium. The initial, the change, and the equilibrium value. All right, so I have run out the clock here, so I'm going to have to go through this very fast. Actually, you know what? If you need to go, that's fine, because I'll post this video. But yeah, I'll work through this here. It'll probably take another like 3 or 4 minutes. But But yes, so I'm going to set up with my, again, I is initial, C is change, and E is that endpoint or equilibrium. I feel like different people says the E stands for different things. So my initial concentration of my ammonia is the 0.188 molar. And I don't start out with any hydroxide ion or ammonium ion in solution. Right? That's the whole idea, is I'm dropping this ammonia into solution and I'm watching what happens when it reacts with water. My ammonia then, since that's what I started with, is going to decrease in concentration, right? I don't know how much it's going to decrease in concentration though. I know it's going to decrease, but I don't know how much. So that's why I'm going to leave that as this variable X, right? So it's going to decrease by some amount, some variable X. That's what I'm going to have to solve for. Importantly, every bit of this base is going to react to form one conjugate acid and one conjugate base. What I mean by that is if I have one molecule of ammonia reacting with water, it's going to produce one molecule of this conjugate acid and one molecule of this conjugate base. So if I have X molecules of base reacting, it's going to produce X molecules of conjugate base and X molecules of conjugate acid. And then to get the E, what we're going to do is sum up our columns, or sum up within a column for I plus C. So this becomes 0.188 minus X, 0 plus X is just X, and 0 plus X is just X again. So these are my variables for my concentration at equilibrium. So I'm going to now plug these into my equations here. Right, that's going to go for that value. This is going to go up here, and this one's going to go over here. I'm going to now substitute those in. And now I have my KB expression, right? So I can replace my value, my KB with what the value that was given was, the 1.76 times 10 to the negative 5. My OH concentration turns into that variable X. My ammonium ion concentration turns into the variable X. What's X times X? That's just X squared. And then lastly, I can replace down here my 0.188 minus X. Oops, it's not going to let me move that. Okay. And now I can punch this into my calculator and solve for the value of X. We have this one last simplifying assumption that we can make, which I sort of had mentioned last time, is not 100% necessary, especially now with calculators being as good as they are, but nonetheless, it'll make our lives a little bit easier, is because this number is so low, anything less than 10 to the negative 3, we can just ignore that minus X right there, because the X is going to be so small that 0.188 minus X is basically just 0.188. And if we make that assumption, it'll make our algebra much easier. So everybody take a second and see if you can't calculate what X would be. This down. All right, so if I punch this into my calculator, sorry, I'm trying to go a little bit quicker. I get my value for X, and I'm going to keep all these digits because I don't want to have a rounding error. I'm going to mark my sig fig with a bar, but I don't want any rounding errors. So I'm going to keep all those digits. And importantly, this is where I think the easiest place to get caught up is forgetting what X is. What did we solve for? X is the concentration of the hydroxide ion, as well as the concentration of the ammonium ion, right? And the one that's going to be important to me in order to calculate the pH is that hydroxide ion concentration. I can get the pOH by then taking the negative log of that hydroxide ion concentration, i.e. take the negative log of X. That gives me my 2.74016. And then I can use the fact that my pH plus the pOH equals 14. So take 14 minus that pOH. And we get our pH of 11.25983. And being good about sig figs, the number of sig figs in my concentration, which was 3, is going to correspond to the number of decimal places in my pH. So that's that value there. Okay, so we have this procedure that we're going to have to do for our weak bases. It's very similar to our weak acids. We're going to first set up our balanced chemical equation. We're going to set up our equilibrium expression. We're then going to do our ICE table so we know what to plug into that equilibrium expression. And then we just got to solve that actual equilibrium expression for X. Then I guess we had this last step to actually calculate the pH, right? Given those concentration values. In this case, it was the concentration of hydroxide ions. So we went to the pOH first and then calculated pH. So then this last one, I'm gonna leave for y'all to do on your own. I just want to kind of take a note about the whole shtick here. Notice here it gave you your Ka, but it's asking for the pH of what's going to be a weak base here, right? The fluoride ion is going to be playing the role of a weak base. So you're going to first have to find the Kb, given that 10 to the negative 14 divided by the Ka is your Kb. And then you're going to do exactly what we did in problem 5. All right, so this is going to be good practice for setting up your ICE tables and everything like that. There will be the answer key posted so you can check your work. Yeah, sorry, this ran a little long. That was my bad. Didn't time it too well, but nonetheless, I will see you all in person on Friday, right? So normal class time, normal class location. I will see you all in 2 days. All right.
Professor, can I ask you a question?
Yeah, totally.
Where can we find these posted lectures at? Because I find them really helpful.
So I haven't posted it yet, right? So basically, I'm going to create a Canvas page and upload it to that Canvas page that I make.
All right.
This is the first time I've recorded one, right? So actually, let me stop recording now. But yeah, so